Hello, algebra friends. I got something fun here. This basis vector, the syntax in geometric algebra, is it's very unique and it's a lot of fun. We're only going to do it in two dimensions to start with, okay? And so we got to remember the rules at all time. A wedge B equals minus B wedge A, and any vector wedge with itself is a zero. All right. So let's start with just E1, E1. Now, these are orthonormal basis of vectors, right? So already we see E1 wedge with self, so that's gone. All right. Now, what's the definition of the dot product? It's the magnitude of vector 1 times magnitude of vector 2 times cosine angle between them. Well, these are unit vectors, so that's 1 and 1. What is the angle between E1 and E1? No, zero. They're on top of each other. So we just get 1. All right. So E1, E1 is equal to 1. E2, E2 equal to 1 also, right? So what is the mixed one, E1, E2? Well, once again, we do the definition of the product. And what's the angle between E1 and E2? Well, they're orthogonal, so it's 90 degrees. What's a cosine of 90? Zero. So this drops out. And we're just left with the wedge, the product, all right? So the product E1, E2 is equal to the wedge E1, E2. And if we swap 2 and 1, remember the rules, we get E2 wedge E1. And it's exactly opposite for E2, E1, which means that E1, E2 is minus E2, E1. So you're going to see a lot of this in geometric algebra. Whenever you swap these indexes, you pick up a negative sign. All right. So we have learned these four things. So we're going to apply these now to something more. So we're going to wedge E1, E2, not wedge. We're going to take the geometric product E1, E2 from the left. Okay. Well, you see immediately that that's 1. That just leaves E2. And here we're going to make the product from the right. All right. So what do? Well, I just swap 1 and 2. When I do that, I pick up a negative. So now E1, E1 is 1. So I get a negative E2. That's all that's left over. Now, let's make the product from the left with E2. Well, it's exact same thing. I just swap these two here, pick up a negative. E2, E2 is 1. So I get a negative E1 is left. And now I'm going to make the product from the right. And that one's easy. It's just E1 because this is 1. All right. Now, here's the biggie. So we're going to take the bivector product with the bivector, the product. Once again, you just swap this. You pick up a negative, and now you've got E1, E1, and E2, E2, which is 1 times 1, which is a negative 1. Okay? So you see these everywhere. When you do them in 3 dimensions, you pick up one more extra called a trivector, and we may get to that. I don't know. All right, so I made this little table for myself. So you can just, real quickly look at this and say, oh, I got an E1 with an E1, E2. What's that? I got an E2 with a E1, E2, etc. So you get all these different permutations of using these three types, two vectors and a bivector. Okay? Now, just for fun, let's do some geometric products in polar coordinates. Here are the basis vectors in polar, the coordinates. If you're unfamiliar with this, I'll leave a link in the description, which shows how these are derived. So let's go look at them. Okay, so we just got a point out here, boom, and we draw a circle that goes through that point. We bring a radius from that back to the origin. So that is the radius of the circle. Now, this radius, it forms a nice angle with this y-axis, okay? And that is our angle theta. And we can move our around, make it smaller, bigger, the angle smaller, the bigger. But the point is, we've got now an angle. So by convention, it's this direction with the x-axis. So we got an angle and a radius. So that's all we need to do the coordinates, okay? So Using those two formulas that we just saw, we're going to put in these basis vectors. So there is ER. Now, the ER basis vector is a unit vector. All right. It is always length 1. It changes directions with R and theta, obviously, but it never changes the magnitude. Okay. And E theta, if I can find it. I'm sorry, I'm so disorganized. Here it is. There it is. Okay. E theta is orthogonal to ER, and E theta changes length and direction. So it does both. Okay. And the magnitude of E theta is always equal to R. You see here, R is 2 and E theta is 2. All right. So that's something unique about it. All right. So let's go back to our doc. Okay. So we want to start taking the product of these polar basis to vectors. So we'll start with ER. So we get ER dot ER and ER wedge ER. Well, we know the rules. Any vector with itself is 0, so we just got to deal with the product, which is just ER squared, right? So we square that, we get the well-known trig identity, which is equal to 1. So ER is equal to 1. All right, let's do E theta. The same thing, that goes to 0. We got this is E theta. We square it. We factor out an R squared. This is the trig identity 1. And we're left with R squared. So that's kind of cool. Now let's do the mixed one. ER E theta. Okay. So we just said these were orthogonal. We looked at them. So that goes to 0. We're left with this. So here is ER wedge E theta. We work that out. All right, we factor out a R and use the trig identity, and we're left with this, which is ER E theta equals R times this bivector, E1, E2. So that's kind of interesting. It's saying that the bivector times R is our wedge, the product. So let's go look at that. Okay, so here's the basis of vectors in polar the coordinate ER and E theta. And I laid it down the flat such that theta is equal to 0, and we can see the radius here is 2, right? So that claim is that the ER wedge E2, this product, this bivector is going to be equal to R. Now let's see if it is. And of course it is. So it is 1 times 2. And this is our bivector unit, our unit bivector, right? 1 by 1. So there's 2 of these here. So it did work. I thought that was cool. All right. I'll see you later.